A production server collapses because 10,000 concurrent requests try to refresh one expired cache key simultaneously. This event is a cache stampede, also known as the thundering herd, where system resources are overwhelmed by redundant, expensive computations. Standard caching relies on a fixed time to live, creating a predictable cliff where data becomes invalid for all users at once. When the time to live expires, every incoming request perceives a cache miss and attempts to trigger the same back-end logic. This surge exhausts database connection pools and increases application memory usage, leading to cascading failures across the entire microservice architecture.
Traditional solutions like mutual exclusion locks prevent redundant work but force thousands of threads into a high latency blocking state. High lock contention during traffic spikes creates long tail latencies, making your system unresponsive even if the database stays upright. Probabilistic early recomputation solves this by introducing a soft expiry window, where recomputation happens before the hard deadline is reached. Instead of waiting for a total failure of the cache, we calculate a probability that a request should refresh the data early. The algorithm depends on 4 variables: the current time, the cached expiry time, the computation time, and a random scaling factor.
The beta factor is a constant that scales the probability. A higher beta makes the system more aggressive in performing early refreshes. Computation time represents how long the backend took to generate the data. This value must be stored alongside the cached object. We multiply the computation time by the natural logarithm of a random number between 0 and 1 to create a stochastic gap. If the current time minus the scaled random gap is greater than the expiry time, we perform a recomputation immediately. By staggering the refresh, only one or a few requests will trigger the update, while the rest continue to receive the stale value.
As we approach the hard expiry, the probability of a refresh grows exponentially from 0% to 100%. This effectively smooths out the back-end load, spreading the cost of recomputation over the duration of the soft window instead of a single point. Even with millions of requests per second, the randomness ensures that the thundering herd is broken into manageable, individual updates. For most applications, a beta value of 1 is sufficient. If your backend is extremely slow, increase beta to widen the safety margin. In systems with heavy database joins or external network calls, a higher beta prevents the expiry window from being too narrow to catch spikes.
You must measure the wall clock time from the start of the backend request until the data is ready to be cached. Most key value stores allow you to wrap your data in a simple object that contains the value and the recomputation duration. Adding a floating point number for the duration increases memory usage slightly, but this is negligible compared to the stability gains achieved. Always use a monotonic clock for measuring delta time to avoid issues with system clock jumps or leap seconds during long computations. When a client requests a key, retrieve the value, the expiry, and the delta time from your distributed cache layer.
If the key does not exist at all, perform a standard blocking fetch. Probabilistic expiry only applies to keys that are still present. Upon a hit, perform the probabilistic check. If it fails, return the cached value immediately to the user with minimal latency. Generate a random float, take its natural log, multiply by beta and delta time, then compare the result to the remaining time to live. If the condition is met, the current request takes on the responsibility of refreshing the cache while the data is still valid. Once the new value is retrieved, overwrite the old entry and update the stored computation time for the next probabilistic cycle.
Because the window is small and random, the chance of 2 requests deciding to refresh simultaneously is extremely low, eliminating the stampede. You can further optimize by returning the stale value to the user while performing the recomputation in an asynchronous background task. In a distributed environment, use a centralized cache like Redis to store the metadata, ensuring all application nodes share the same expiry view. Implement the probabilistic logic in a Lua script directly on the Redis server to minimize network round trips and ensure atomic execution. The Lua script fetches the value and performs the math locally, returning either the data or a signal that a refresh is required.
Serving slightly stale data for a few milliseconds is almost always preferable to a complete system outage or timeout during a stampede. In Kubernetes, you can implement this logic in a sidecar proxy, transparently protecting your main application from thundering herd effects without code changes. Probabilistic expiry reduces the variance in response times, allowing your load balancer to distribute traffic more evenly across the cluster. Monitor your cache hit rates during peak traffic. A healthy probabilistic system will show a stable hit rate even when keys expire. If you see periodic spikes in database CPU usage that align with your cache time to live, you are likely suffering from stampedes.
By eliminating the lock wait times, the 99th percentile latency will drop significantly, improving the perceived performance for all users. Reducing the peak load on your database allows you to provision smaller instances, directly lowering your monthly cloud infrastructure costs. Use mutexes only when absolute data consistency is required, and stale data is strictly forbidden by the business logic. Product catalogs, user profiles, and social media feeds are perfect candidates for probabilistic expiry, where high availability is the priority. The method is less effective for very low traffic keys, where the probability of a request falling in the soft window is statistically low.
Log every early recomputation event to verify that your beta parameter is tuned correctly for your specific traffic patterns. Measure computation time, store it as metadata, implement the random logarithmic check, and monitor your backend load during peak hours. Moving from static to probabilistic expiry transforms your caching layer from a potential point of failure into a robust shield for your backend.